Okay, I think, yeah, recording has started. So this is going to be lecture 2, part 3 of Signals and Systems. And hopefully you have the time to watch lecture 1s and lectures 2. I'm doing a different part system with this course. I'm kind of splitting the lectures into smaller sub-lectures because I feel like there's a lot of material and it might be more productive to break it down into smaller chunks so it's easier for people watching to understand and then just absorb all the information. So today we're going to talk about the general form of complex exponential signals. So just taking a look at this, suppose we have a signal of the form, or not signal, it could be a function even of the form c alpha to the n. And the c is a complex number and it's given as such, where you have the absolute value of c, that's your magnitude, and then you have the phase factor here. Okay, and then alpha is also a complex number, given in the form of magnitude and then the j omega 0 at the top. Now, let's say you take these complex numbers and then you plug it into your original complex exponential signal. Let's see what happens. So you replace c by mag c e to the j theta, and then you replace alpha by mag alpha e to the j omega 0. Now, this alpha is taken to the power of n, so everything here, which is your alpha, that's going to be taken to the power of n as well. And now, using power law, you can split the n into the two different components that you have in there being multiplied. So you have this stays the same. You have mag alpha to the n, and then e to the j omega 0 n. And now you can take this and this, you bring it to the front, and then you combine the exponential together so you have the same base. So the exponents are going to add. So then this is what you have. Now, just a little quick reminder is when you have an exponential in this form, e to the j theta, well, you can apply Euler's relation. If you forgot, you can go watch the previous lecture from intuition, but here it is regardless. You should have this memorized. It's very, very important. So e to the j theta is cos theta plus j sine theta. In this case, we don't have theta, we have omega 0n plus theta. So this is going to be our overall, let me call theta prime, for example. And so you can convert this complex exponential to a sum of trigonometric functions, complex trigonometric functions. So you have this plus j sine omega, blah, blah, blah. So you convert this to the Euler's relation between a sum of a cos and an imaginary sine. And now you take that, you plug it into here. So this is what we have there. And now all that we have is I'm just going to take this, I'm going to distribute it through the brackets, and then this is what we got, and this is what we got. Okay, so we have a real part, as you can see, and then you have an exponential, imaginary part. Now, what's the point of doing all of this? It's I'm gonna give you a little bit of a preview, maybe a little bit of a foreshadowing. If you look over here, your real part is a function of n, right? It depends on time. So you can see that it has some sort of, if you look at this intuitively, right, just the real part here, you have a cosine. Well, a cosine is going to repeat itself. So you can kind of see that there's a periodicity of a function, okay? So you have a cosine function, right? A cosine function is going to be repetitive. So you're going to have something like this. What am I doing? Something that looks like this. Oh my God. So something that follows this nature. So let's say you have this, but it's not going to be continuous, it's going to be discrete. So there we go. Only the vertical lines is going to look like that, okay? Now, what's the, we know that the period, we know that this function is going to be periodic, but what about the amplitude? How's the amplitude going to change as a function of time, or does it have any time dependence here? If you look at the amplitude, you have the complex value c. Well, if you take the magnitude of that, it's a real number. So this is just some real number. So that doesn't change anything at all. Okay, it's just going to keep the amplitude the same c. But this alpha to the n here, that changes things because it's an exponential. So as your function is being sinusoidal and you have we have an exponential in front of it, that exponential function is also a function of the same time that your sinusoidal is a function of. You understand? So you have your sinusoidal that's kind of doing this. But the amplitude, let's say it doesn't go from -1 to 1 anymore, it's going to go by alpha to the n. Forget about the c. Good job. 이제 뭐지? Sorry about that distraction. I'm not about to restart this video anyways. We're just going to keep on going here. Okay, so what do you have? What was I saying? Yes, your your exponential function is going to be the amplitude of your trigonometric function, okay? So this is what we have. The same thing for the imaginary part as well, but it's, instead of a cosine, you have a sine. But again, the amplitude is going to change exponentially. But now you have different cases you can consider. You can consider that your alpha is equal to 1. What happens when your alpha is equal to 1? Well, 1 to the n is still 1, so that doesn't change. So then you're going to have a cosine plus a j sine. And the amplitude is just going to be the magnitude of c in this case. So you don't have that exponential dependence of your amplitude, okay? But now you have multiple cases. Alpha could be greater or smaller than 1. We're going to consider both cases here. Let's say alpha is smaller than 1. Okay, so if you've studied, you probably studied this in high school when you have a negative value raised to an exponent, okay, well, it's going to be a decaying exponential, right? It's going to be a decaying exponential. So, okay, this alpha, magnitude alpha to the n is going to be decaying exponential. Same thing here, it's going to be a decaying exponential. So the way you can kind of visualize it is you have a sinusoidal signal that's being constrained by some decaying exponential. And what is a decaying exponential? You start at a certain value and then you go, phew, you just go like this. This is all it is, okay? But now you got to understand that sinusoidal function, it goes above and then it goes below the x-axis as well. Like this is your middle, so it goes up, down, and keep on going. So your decaying exponential is going to be on top and it's going to be on the bottom. And that's going to be kind of like the envelope of your sinusoidal function, okay, is going to limit that amplitude in that sinusoidal fashion. So if I were to plot my decaying exponential first, it will look like something like this. That's your decaying exponential alpha to the n here, okay? And now your sinusoidal function can only go so high. And how high can it go? It can only go as high as predicted by this exponential decaying function, okay? So that's the intuition behind it. And you can see that the sinusoidal signal here is in green and the decaying exponential is in orange. Now, the opposite of a decaying exponential is you have a growing exponential, okay? And what is that? If alpha is greater than 1, then you have a growing exponential, okay? Again, this is just high school math. For both cases, for the real part and for the imaginary part. So now you have a sinusoidal function, a signal that is constrained by a growing exponential. So you have an exponential function here that's growing. And your sinusoidal function is just going to be limited by that growing exponential. That's all it is, okay? Now, why am I doing all this and what's the point of all of this? It's very important when you study courses with a lot of math to really lay the foundation, because whether you like it or not, electrical engineering or signals communication theory is basically math, okay? We want to be able to be very good at the math so we can apply it efficiently and have a deep sense of understanding about the complex numbers, periodicity, exponentials, trigonometry, and all that kind of stuff. So you should be able to switch from Euler's notation to trig, and trig back to Euler's notation, and back to complex number format, back to polar form, and all that kind of stuff. It needs to be at your fingertips. You need to really know how to do that. And the best way to do that is to do these kind of analysis, right? Very good. It's very different from a circuits-based class where you really need to understand the underlying mathematics is really, really important. You can't, it's not a class where you can just grind examples and you're just going to be able to do okay. Not necessarily, because if you change a small thing, yeah, the whole question's changed, right? It's not like circuits. This one, you really need to take a minute. I know it's annoying, but take a minute and understand the math and make sure you're up to date with everything that's going on. So that's why we do this. Okay. Now, when you're dealing with discrete time exponentials, you only consider a frequency on the interval 2 pi. That's just standard. So you can go from 0 to 2 pi for your frequency, or even the frequency range, or you can go from minus pi to pi. Now, what is the condition for x of n equal to e to the j omega 0 n to be periodic with period n greater than 0? So I'll let you think about that for a minute. Don't look at the solution while I grab a my protein shake. Yeah, we don't have tea today, we'll have protein shake. While you're thinking about the question is, a good workout, hit back and biceps this morning. Absolutely destroyed them. So we gotta replenish. Ate some good food. And now it's about nighttime where I am. 5 p.m. and I record these, go to bed. Tomorrow we hit shoulders and abs. Get back to business. X of n is equal to x of n plus n, where n is your period. That's your condition. If you have no idea where this came from, I invite you to go watch the previous lectures. One of them, I'm sure I've talked about it a lot, okay? So I'm just going to take this and I'm going to apply it to my exponential here. So we have e to the j omega 0 n plus n, where big N is your period that you want to find, okay, essentially. Okay. So as soon as you do that, you can split the exponential into two parts because of power laws. So you have e to the j omega 0 small n, e to the j omega 0 big N, okay? And this definition tells you that this addition or this shift by the period of your signal is equal to the original signal itself. So this is my shifted signal. I'm just going to equate that to the original signal e to the j omega 0 n. And as you can notice, this and this will cancel out, which means that my e to the j omega 0 big N has to be equal to 1. Okay. Now, again, Euler's relation, it comes up again. So you have e to the j omega 0 n. Well, this can be expressed as a sum of a cosine plus j sine. Okay. So here I have this. Okay. Now, this number 1 here, of course, it's a real number, but you can pretend that the imaginary part is 0. Actually, not pretend. The imaginary part of this real number, of this complex number, I should say, is 0. So you technically have 1 plus j 0. And if you've seen anything from linear algebra, so if you have a plus jb equals 1 plus j2, for example, a has to be equal to 1 and b has to be equal to 2. Okay? But in this case, we don't have a plus jb, we have cosine and we have sine. So if cosine something plus j sine something is equal to 1 plus j0, then the cosine has to be equal to the 1 and the sine has to be equal to the 0. So my cosine has to be equal to 1. And for this cosine to be equal to 1, high school math tells you that omega 0 n has to be a multiple of 2 pi. That multiple, I'm just going to call it an integer value m of 2 pi, which is right here. Okay? So that means that my omega 0 n, well, I just did this. I just have this in a little bit of a note here. Omega 0 n has to be a multiple of 2 pi, where m is an integer. Okay? So this is what we have. Now I can rearrange this equation, and this is my condition. Omega 0 over 2 pi is equal to m over n, where m is your integer and n is your period. So the fundamental period of the signal, which is n, if I isolate correctly, I get that this is my answer. Okay? So you can see that n is equal to m 2 pi over omega 0. But understand that we're in discrete time domain, and your period has to be an integer. Now, before we move on, I want you to think, all right? You got to use your brain. Here's what I want you to think. How is it possible that we have a pi here and we expect m to be an integer? I'll give you a hint. We have a pi here, and then we have an m here. That m is an integer, but overall, if we do this, how are we going to have n be an integer? How are you going to do that? So pause the video and think about it. Okay, assuming you're being honest and you pause it and you're back now. Well, if this is an integer, this is an integer, pi is not an integer, okay? But if you think about frequency is almost always expressed in terms of pi. So if you have omega 0 equals to k pi, something like this, okay? Then you have m 2 pi, sorry. So you have omega 0, let's say for example, is equal to k pi because frequency is almost always expressed in terms of pi. Then n is equal to m 2 pi, and what is k omega 0 is just k pi. So assume that this is an integer right now, right? It's an integer. So then you have pi over pi. An integer times an integer over an integer is an integer, okay? So that's how your n is an integer. So it's very good to pause for a second and ponder upon these definitions, because as you just seen, right, it makes you realize that, oh, okay, the only thing that's going to make n being an integer here is that my frequency has to be a multiple of pi. If that's not the case, then I can't really have a period because my period has to be an integer. You see how the integration works? And now if you were to be the type of person who just kind of goes and then you just going to grind examples and you don't stop to take a minute and ask yourself, okay, what did I learn from this? Well, you're kind of screwed, because this is how profs get you, especially in this class. And, you know, this class is difficult. So it's very good to get the foundationals right on point. Okay? Very important. So now we're going to do a couple of examples here, because examples is how we can understand things better. So example 1 is determine the fundamental period of the discrete time signal x of n, which is equal to e to the j 2 pi over 3n, e to the j 3 pi over 4n. So we want to find the fundamental period. Okay, so how are we going to do this? So we have x of n, which is equal to this plus this. And all I'm going to do is I'm going to take this one, and I'm going to call it x1. And I'll take this one, and I'll call it x2. So x1 is equal to e to the j 2 pi over 3 times n. And omega 0 is 2 pi over 3 in this case. Here you had omega 0, but in this case, omega 0 is 2 pi over 3. Now I'm going to take this equation right here for n, and I'm just going to replace stuff. So I have n1, which is equal to m, 2 pi over omega 0. Or what is omega 0? Is 2 pi over 3. So the 2 pi's and 2 pi's are going to cancel. So you have 3m. Now you want to pick the m value that makes n the smallest integer possible. In this case, the smallest integer m that makes n the smallest is 1. So you have n equals to 1 when m is equal to 3. So your n1 is equal to 3. So the condition for your x of 1 to be periodic, it means that n1 has to be equal to 3. Okay. Now do the same thing for x2. So x2 is equal to e to the j 3 pi over 4n, where omega 0 is 3 pi over 4. So n2 has to be equal to m 2 pi over omega 0, replacing my omega 0. The pi's and the pi's cancel, so you have m, which is equal to m times 8 over 3. This is your n2. And now you want to pick the value that makes n the smallest value possible, right? And in this case, if m is equal to 3, then you have 8, which is the smallest value possible, all right? So n2 is equal to 8 when m is equal to 3. Now, notice you have two periods. You have n1 and n2, but you want to find the overall period, fundamental period of your complete function x of n. So how are we going to do this? It's pretty simple. This goes back to middle school math now. I feel like we're going retro. Yeah. So if you kind of got messed up, you didn't pay attention in middle school, then I don't know, signal system is going to be hard. I'm just joking around at this point. I'm bored. Okay. So how do you find the least common? How do you find? Okay, I kind of spoiled it, but the overall fundamental period is going to be the least common multiple of these two. Now, I forgot how to do this in high school, in middle school, the way the teacher taught us in a simple way. So we're just going to kind of memorize the formula here to do it for us. So the least common multiple of n1 and n2. Suppose you have two numbers, a and b. So the least common multiple of a and b is going to be the multiplication of the two numbers divided by the greatest common divisor of the two numbers. So let's look at an example here. What is the greatest common divisor of 3 and 8? What is a number that when you take the number 3 and you divide it by that number, it divides evenly, right? So you don't have any remainders, right? It's a complete whole number. What is a number that divides both 3 and 8 that gives you a complete whole number, and you want that divisor that you're dividing by to be the biggest number possible? In the case of 3 and 8, the biggest common divisor is 1. When you take 3, you divide by 1, you get 3. All right. When you take 8, you divide by 1, you get 8. If you were to pick 2, for example, 3 divided by 2 is not a complete whole number, so it cannot be 2, right? Even though 8 divides by 2 is 4 is a complete number, whole number, all right? That's why it's 1 in this case. So applying the formula, 3 times 8 is 24 divided by 1, so you just have 24. So this is your fundamental period. Okay. Now, is x of n e to the j 2 over 3n periodic? Now, I want you to pause this video again and ponder about it. A little bit of a hint is I explained the theory a little bit earlier, and I made you pause again. So now is your chance to apply it. Okay. If you paid attention, then this is not periodic. Why? Because there should be a pi here that makes it periodic. Okay. So that now you can see how this could save you a lot of time on an exam or a test when you're trying to prove periodicity. You could go straight to the answer here while being intuitively and mathematically correct by just writing a simple line. Why? Because you spent some time and pondering upon that theory. If you did not do that, you're going to have to do the math. And in a class like Signals and Systems, you don't have time to waste, all right? So again, here, for the sake of proving this example, we're just going to do the example itself. So omega 0 is 2 over 3, okay? So n is equal to m times 2 pi over omega naught. This is the formula we derived earlier, okay? We're just going to replace omega naught by 2 over 3. And you can see that the 2's are going to cancel, but you have 3 pi times m. Now, there is no possible integer value of m that makes n an integer, so the signals is not periodic, okay? That's it. So now let's look at the last example here. Okay. Actually, I want to maybe pause the video and you try it by yourself, and then you can fact check with me here. Okay. Um. Okay. Is x of n e to the j 3 over 5 pi times n or plus e to the j? Yeah, I already noticed a big blunder here. What am I doing? This is on top. This pi has to be on top. Well, this is what happens when I'm making my own notes. Guys, whatever you're reading here is me writing up my own notes. There's no like plagiarism or whatever. I'm not trying to get into problems. We're trying to help out people. So it takes a lot of work to write these things. And a lot of it comes from the time when I was taking the class. So that's how it was. I have some notes when I was in class and then wrote up some stuff. And this is what I use for a reference because it helped me and I think it would help others too. So that's how I do it. Let me just fix this blunder. There we go. This should be it. I want to apologize for this. Okay, so this is your signal. And again, you have 2 parts. You have this one plus this one. So I'm just going to call this one x1 and this one x2. Now, so this is x1. Now you can extract your omega 0 from the signal. And omega 01 is 3 pi over 5. And omega 02 is 5 pi over 7. Applying your formulas, if you do the same thing, I'm not going to repeat it. You get n1 is equal to 10. And applying your formulas, you get n2 is equal to 14. The greatest common divisor for 10 and 14 is 2. Okay, and the least common multiple here, applying the formula I talked about, is the multiplication of the 2 divided by the greatest common divisor. So you have 14 times, you do this in your calculator, you get 70. Okay, so this is your fundamental period, which is 70. Why is pouring like crazy right now? Oh my god. Check the weather. Insane. Okay, last part. Harmonically related periodic exponential. So you have, what is this? This is phi? Yeah, this is phi. Phi of kn, which is equal to e to the j k 2 pi over n times n. Now you can notice that we have a k factor here as an integer. So you're not just looking at some regular exponential, you're looking at a harmonically related exponential. So you have, what is this? For k equals 1, you have the first harmonic, and then k equals to second harmonic, and then 3, and then 4, and then 5, and all that kind of stuff, okay? Just by changing the values of k. And now if you take k and you change it by the period, okay? This is what phi k of n is. So phi of k plus n of n. Okay, this is what it is. If you take your harmonic and you shift it by the period, this is what happens. So you have e to the j kn plus k plus n times 2 pi over n times n. Okay, so you're gonna break that exponential into two different parts using power laws, and you have e to the j k 2 pi over n times n, e to the j n 2 pi over n n. So these two n's, your period, are gonna cancel out, and then you have this, which stays the same here, and then you have this, where n is an integer. Okay, now again, you can take this exponential and you can express it into the form of a cosine plus a j sine, where this is your theta and 2 pi. Now, a multiple of 2 pi for a cosine is 1. So this cosine is just going to be 1. And a multiple of 2 pi for a sine is 0. So in the end, this whole thing here is just 1, which means that everything that you have here is equal to this part only. And if you counter and you go back to what this part is, and you go here, you're like, whoop, it's equal to the same thing I started with. Oh, bingo, baba, ha, there we go. So this is it. So moral of story here, if you have a different, if you take a harmonically, the kth harmonic of your signal, you shift it by the period, it's still equal to the kth harmonic signal itself. That's the takeaway here. Okay, I don't recall having this part that's adjusted here being very, very important, but it's good to know. Okay, so that's it with this lecture. And then the next lecture, we're going to go into lecture 3. Part 1, 2, and 3 of lecture 2 is done. Thank you. And then if you have any questions, you can put them in the comments. And I always enjoy reading the comments. Thank you very much.